Today we're going to be talking about patterns and inductive reasoning, which are some of the basics of geometry. Now we're going to be looking at these patterns, and you're asked to sketch the next figure in the pattern. So here we have one square, and in the next figure we have two squares horizontally, two vertically. Horizontally going across vertically up and down, three squares vertically, three horizontally with the piece in the middle. And we'd like to figure out what we think the next figure would be. Well, if it goes 1, 2, 3, the next one should have 4. Do not laugh at my drawings. They are not terribly artistic, but let's see what we can come up with, at least an approximation here. So here is 4. Now it looks like this one should come out, and we should have another group of squares going down. These aren't terribly straight, but you get the idea. And it looks like that each set comes out to make another group coming down. And here we have, so at least this is a rough sketch of what this should look like. And I'm sure you can probably do a much better job on your outlines at home. Next, another look at patterns here. We'd like to predict the next number in the pattern. Well, it looks like this one is going up by 10, so let's try that. So 10, 20, 30, 40, so the next one would be 50. So going up by tens. Now this next one, let's see how this is working. Now it looks like there's between 1 and 2, there is 1. Between 2 and 4, there's 2. Between 4 and 7, 3. Between 7 and 11, looks like we add 4. Between 11 and 16, we add 5. So probably for the next one, we would add 6. And we would get 22 for the next number. So let's look at the next pattern here. We have 1, 4, 16, and 64. Well, how are these numbers related? Well, it looks like if you multiply the first number by 4, you get 4. The second number, 4, you multiply by 4 and you get 16. 16 you multiply by 4 and you get 64. So we probably have to multiply by 4 again to get the next term, which would be 256. Next, we have -5, -2, 4, and 13. So let's see how these are related. It looks like in the beginning, to get from -5 to 2, we add 3. To get from 2 to 4, we add 6. To get from 4 to 13, we add 9. Excuse me. And to get from 13 to the next number, what do you think we'll add? Well, looks like we're going up in increments of 3. Let's add 12, so we will get 25. All right, so now let's move on to the next page. And here we're looking at some definitions. Inductive reasoning is making conclusions based on observations. In other words, we were looking for patterns. We recognized the patterns that we were looking at in the last set and drew the conclusion as to what our next number or our next figure should look like in the pattern. A conjecture is an unproven statement based on observations. And a counterexample is an example that shows that a conjecture is false. And we're going to look at examples of these things to help make this more meaningful and help you to understand it. Here's an example of a conjecture. For all real numbers x, the expression x squared is greater than or equal to x. And initially you might be saying, well, yeah, that makes sense. Like if I have 5 squared is greater than or equal to 5, and because 5 squared is 25. And yeah, that would work. That is true. But is there a counterexample? Is there something that would prove that false? And let's think about numbers that are not whole numbers. How about numbers that are smaller than 1? Let's say that I chose x to be 0.5. So think about it. X squared would be equal to 0.5 times 0.5, so that would be 0.25. So here is a case where now our conjecture said that x squared should be greater than or equal to x. So is it true that in this particular case, when x is 0.5, that 0.25 is greater than or equal to 0.5? No, not at all. That's not true. In fact, we should put a slash through that. So this is a counterexample. This shows the conjecture is false. So a counterexample is just an example to show that this conjecture can be false. Okay? So let's move on with some more examples. Here's another conjecture. You put that back. There we go. For all real numbers x, the expression 2x, let's try this again. For all real numbers x, the expression 2x is greater than or equal to x. So we want to find a counterexample. So remember, this is the original one. We want to say that 2x is greater than or equal to x. Now let's see if we can find an example where this is not true. What about if I chose x equal to be -1? So let's plug -1 into our expression 2x greater than or equal to x. Let's see, does it work? 2 times -1, is that greater than or equal to, I'll put a little question mark, -1. 2 times -1 is -2. Is -2 greater than or equal to -1? Think of your number line. Here's 0 and +1. We go -1, -2. Wait a minute. The numbers further to the left are smaller. So -2 is not greater than or equal to -1. So here is your counter example. So this shows that in this case, 2x is not greater than or equal to x. So you just proved that that conjecture was false. So next, for all real numbers x and y, if x is greater than y, then x squared is greater than y squared. And we want to find a counterexample. So we got to pick some numbers. So we're saying, let me write this out. If x is greater than y, then x squared is greater than y squared. So what about if I chose numbers such as, let's say I chose x equals -1 and y equals -2. Let's see if that would work. Is it true that x is greater than y? That part, -1 is greater than -2. Yep, that works, so that's good. Now, is it true then that x squared is greater than y squared? Let's see. We have -1 squared is greater than -2 squared. Do put your negatives in parentheses if you're going to square them, because you need to square that negative too. So -1 squared gives you +1. -2 squared gives you +4. Is 1 greater than 4? No, that's not the case at all. So you just showed that here was an example where when x is greater than y, x squared is not greater than y squared. So in this case, x squared is not greater than y squared. You just gave a very good counterexample. All right. Now remember, this is also very important. Just looking at several specific cases This is inductive reasoning. Does not prove your conjecture. Okay, you can't say, well, here I've got 5 cases where it works, so we're done. I can say that it's true. No, because sometimes you can come up with a counterexample. Just looking at the instances where it does work is not enough to prove the conjecture is true. So thank you very much for joining me today. I'll see you next time.